Hi, welcome to video 2 on option D, drugs and medicines. Today we're going to talk about antacids and analgesics. Antacids are very straightforward. There are medicines that are used to treat dyspepsia, which is just the excess production of acid in the stomach, and also acid reflux, basically the sense of heartburn when you have acid entering the esophagus. The reason why we experience heartburn is that the stomach itself has a protein lining that is it's pretty stable and does not get irritated by the very low pHs of the stomach, around pH of 1. But the esophagus does not have that, and so when any acid can travel up, as you can see here in this area, if the acid is traveling up, you're going to find that that area is going to be irritated by that, and it's going to hurt, and that's why it causes what we call normally heartburn. All right. So how do antacids work? They're going to neutralize that acid. So you're going to have 3 different components. The first component is very obvious. You're going to have a weak base. The reason why we use a weak base rather than a strong base to neutralize the acid is that strong bases can also hurt tissues, and so we don't want any base that will release that will act as a strong base. So we can use hydrogen carbonate, in this particular case sodium hydrogen carbonate, or calcium carbonate, 2 weak bases. And then we can use aluminum hydroxide or magnesium hydroxide as well, which are weak bases. You may wonder, why are metal hydroxides considered weak bases? And the reason is because they are mostly insoluble, so they cannot release the OH until they react directly with an acid. And so very little OH is going to be in solution, so it will not react with your esophagus. But once it's in the stomach, it will react with the stomach acid, mostly composed of hydrochloric acid, to give you the neutralization products. You do need to know these products. You need to make sure that you are able to balance, and to remember that if you have a carbonate or a hydrogen carbonate, your products are going to include water and carbon dioxide. Depending on the weak base present in your antacid, you will be able to neutralize more molecules of stomach acid per mole of weak base. All right, so make sure that you notice that. Here we can see that aluminum hydroxide can neutralize 3 molecules of hydrochloric acid versus 2 molecules of hydrochloric acid that can be neutralized by magnesium hydroxide. Some of the weak bases have side effects. Aluminum tends to cause constipation, while magnesium tends to be a laxative. So many times those 2 are combined. A common example of a drug that combines the 2 is Maalox, that contains both magnesium hydroxide and aluminum hydroxide, and that way you don't have so many stomachal problems afterwards. A second component that you must have on the inside of your antacid is the antifoaming agents, in order to reduce bloating and flatulence, because sometimes the products of neutralization will have the formation of gas, and so you want to minimize that. Dimethicone, all right, it's an important substance that you need to know is going to be your most common and very efficient antifoaming agent in your antacid. Finally, you have things that are called alginates. Alginates tend to float on top of stomach acid. They form like what is called a raft, and they act as a barrier to prevent acid from moving upwards and refluxing into your esophagus. All right, and because they are slightly thicker, they also help coat the esophagus with some of the weak base for it to react and actually neutralize any acid that may have gone to the esophagus. If you may look at the drawing that we had here, if you put the alginates would block there and stop the acid from moving into um, the esophagus. And that's basically antacids very quickly, all right? So just remember, weak bases, antifoaming agent, and alginate, and remember to look at the stoichiometry of your chemical reactions. Analgesics are a different type of drug. Analgesics are drugs that are painkillers or pain relievers, and they basically reduce or inhibit the perception of pain. They tend to not have an effect on the cause of the pain or the injury, but they will minimize our sensation of pain. All right? And how does that work? Our body, our nervous system, has pain receptors throughout the body, which are activated by or stimulated by prostaglandins. All right? Prostaglandins are chemical messengers that are found and released by damaged cells. All right? Here are some general structures of prostaglandins. Don't worry too much about the structure. We won't really be needing them, but it's just so you can see that these chemicals are what are there. Now, prostaglandins are released by damaged cells and are responsible for what we call the inflammatory response. Inflammatory response includes swelling. All right, prostaglandins will cause increased blood flow, and that swelling will allow for more white blood cells to come and infiltrate through the tissues. But it also swells to immobilize. For example, if you have a joint problem, it will swell that so you don't move that joint in order to try to protect the area. You'll have also, they also cause the increase in temperature, what we normally call fever. That's in order to have the reactions happen quicker. So basically, if you're doing an immune response, you want the rate of that reaction to be faster. So that's why we have an increase in temperature. And obviously, they're also responsible for pain sensation, which is in order for you to remove your hand or an injured part from whatever is causing that injury. That's why we sense pain when we put our hand on a fire or something like that. So an analgesic must be able to stop the pain message from reaching the brain and actually being perceived, being analyzed as pain. So there's two general mechanisms through which this happens. Mild analgesics tend to do this by blocking prostaglandin production at the site of injury. So the prostaglandins are not released, or they are broken down, and therefore they cannot activate the pain receptors. All right. Mild analgesics are known normally as non-steroidal anti-inflammatory drugs, or NSAIDs, and they tend to be excellent at stopping mild pain. Being anti-inflammatory, they reduce the inflammation because they stop the inflammatory response, and they're also antipyretic, i.e. they reduce fever. One particular mild analgesic, paracetamol, known as acetaminophen here in the US, is a mild analgesic that acts by inhibiting prostaglandin release in the brain, all right, rather than at the site of injury. Prostaglandins cannot cross the blood-brain barrier. We'll talk more about that in further videos, or later in this video itself. But prostaglandins cannot cross that barrier, so they must be re-released in the brain. Paracetamol stops that release in the brain, so paracetamol is not able to stop swelling like other NSAIDs can, but it still can relieve pain, mild pain, and it can still act as an antipyretic because temperature regulation is controlled in the brain, all right, or in the upper nervous system. Strong analgesics, and we're going to talk about opioids or opiates, all right, actually act in a different form or fashion. They act on the brain itself, and they literally block the pain receptors, all right, and therefore by blocking the receptors that where those prostaglandins would actually bind and stimulate the sensation of pain that then would be analyzed by the brain as that message that is pain. these analgesics will bind there and block the prostaglandins, and so we do not feel the pain at all. All right. These strong analgesics also have an effect on your alertness and the mood, and because they affect your brain and your perceptions, they are considered narcotics. All right. Any substance that affects your perception by acting directly on your brain is considered a narcotic. So let's go ahead and look at some of those different analgesics. All right. The analgesics that you're going to use are going to be depending on the type or severity of your pain. For mild to moderate pain, you're going to use mild analgesics. We're talking about aspirin, ibuprofen, paracetamol, things like that. As the pain persists and becomes stronger, you're going to use mild opiates or mild opioids. All right. Like codeine. If the pain continues and it gets stronger and stronger, you will need to use a stronger alternative, and you will use some strong opioids, all right, such as morphine. In some countries, it is legal to use heroin, but that is not everywhere, so that's not as common. And the reason for that is because any of the strong opioids have a risk of dependence. So normally you will try to use the mildest possible analgesic before moving on. And obviously the strongest ones are prescribed and must be administered by medical professionals. All right. So if we're looking at mild analgesics, let's start by looking at aspirin. Aspirin, otherwise known as acetyl salicylic acid. All right. Acetyl salicylic acid is a derivative of salicylic acid, as salicylic acid is a natural compound found in willow bark, and it's been known since antiquity to act as an analgesic to relieve pain. The problem with salicylic acid is that it's very acidic, all right, and it causes bleeding of the gums, it caused bleeding of the stomach, and so eventually, luckily in the 1800s, a derivative made by Mr. Bayer, yes, famous from aspirin, all right, was made, and this ester derivative blocks this OH group over here, and we put an ester, we put an acetate group or ethanoate group there, all right. If you want to see the structure with all the carbons, it would be a carbon here, and this would be a CH3, all right, and at that particular point, it makes it a lot less acidic, less irritating. You can take it, and it does not irritate your stomach as much, even though it still does that. Once it is absorbed and it moves into the small intestine, the alkaline conditions of that will break the ester. You'll reform salicylic acid, which is absorbed by the body and acts as the analgesic. All right. Now, some of the side effects of aspirin include decreased blood clotting and blood thinning. All right. They can cause irritation to the stomach and to the small intestines, even though it is less than salicylic acid. It's still quite acidic. If you take it in excess, you could have acidosis of the blood, which is lowering of the blood pH. It can cause, in some people, allergic reactions. Some people are allergic to aspirin. And in children under the age of 12, it can lead to something that is called Ray's syndrome. And Ray's syndrome is a rare liver and brain disorder that can, if it happens, lead to death. All the different side effects that we experience or we see for aspirin can be increased by synergistic effects with alcohol. Synergistic effects just means that when acting with something else, it will cause the effects to be more marked. Another analgesic that we can use is ibuprofen, very similar to the action of aspirin. It also is acidic, as you can see that it has a carboxylic group here. And so it's still going to be quite irritating to the stomach, even though it is milder than aspirin. It also has synergistic effects with alcohol, but different than aspirin, it does not cause Reyes syndrome. Paracetamol, and by the way, the structures of both aspirin, ibuprofen, and paracetamol can all be observed in your data booklet. All right. Paracetamol, marketed as Tylenol, is a mild analgesic that is very safe to use. It's less acidic if you're using it in normal doses. All right. It has very few side effects. It does not cause Rey syndrome. It is mild to the stomach. It's non-allergenic. So all of these things make it excellent. Unfortunately, chronic use and overdoses can have severe liver, kidney, and brain damage, and similarly to aspirin and to ibuprofen, if taken with alcohol, it can significantly increase these toxic side effects. All right. When we look at strong analgesics, we are looking at opioids, derivatives from the opium poppy, and these particular substances are alkaloids. Alkaloids means that they are plant derivatives, all right? They're basic plant derivatives that contain a heterocycle and a tertiary amine. Okay, wait, what does that all mean? All right, so if we are looking for a heterocycle is a ring that is composed of carbons and any other elements. We happen to have, in this particular one, if we're looking at morphine, we're looking at two different rings that are heterocycles. We have a ring there that is composed of carbons and oxygen, a 5-member ring, and we have a 6-member ring there that is composed of 5 carbons and 1 nitrogen. So those are the heterocycles. But that second one I am going to remove because I want to focus on something more important. I'm going to focus that that particular nitrogen there also is a tertiary amine. That means that the nitrogen is directly connected to 3 different carbon atoms. All right? So when we have these characteristics, that is plant-derived, that is basic, that it contains a heterocycle and a tertiary amine, we have the compound being an alkaloid. All right? Now, opioids act directly on the central nervous system, all right? And they act on the brain. They have to be able to go through the blood-brain barrier. The blood-brain barrier is a fatty tissue that separates the normal bloodstream from the brain in order to protect the brain from getting infected by other substances. All right? So in order to act on the brain, a drug must be able to go through the blood-brain barrier, or in short, the BBB. All right? And let's look a little bit about the structure of this. If we look at the structure of morphine, again, you have it on your data booklets. You'll see that it's mostly carbon and hydrogen bonds, so it's going to be relatively nonpolar. But it has 2 hydroxide groups, one here in blue and one here in red. It's got a little bit of an ether here with the oxygen that is bridging 2 carbons, and you have an amine. So it's going to have some polarity, and the hydroxides in particular make it polar enough that slows down the passage of morphine through the BBB. So the 3 most important opioids that we're going to study are morphine, that is natural, it's taken from the poppy, the opium poppy; codeine, which is found in smaller percentage as in the poppy seed, but it also can be modified from morphine; and then heroin, which is normally produced from morphine by doing esterification. All right? So notice the differences. The structure is generally the same. Morphine, being the natural one, has 2 alcohol groups. One of those alcohol groups is modified into an ether group for making codeine. And in the case of diamorphine or heroin, those groups are esterified by putting ethanoates. Those will change the polarity overall of the entire molecule, each one of those modifications, and make it more or less effective. Codeine is normally a moderate painkiller. It's used in second stage painkiller management. It's used in dental surgeries, cough syrups, and it's a short-term antidiarrheal. We'll talk a little bit about that in a moment. Morphine is used as a strong painkiller, third stage management. We remember the stages that we were talking about before. It is used for major surgery, people who are suffering from pain of cancer, major trauma, fractures, all of these kind of things. And then heroin is normally used as an illicit drug, but in some countries it is used in palliative care. Palliative care is when you cannot help a person any longer, but you are minimizing the pain they feel. And so you can actually give these very potent drugs. All right, so here are the painkiller effect increases as we go from codeine to morphine to heroin, and so do the side effects. So here are some of the side effects of opioids. All right, constipation, cough suppressant, pupillary constriction, and then they also have narcotic effects, and we're going to focus on the narcotic effects of heroin. When people first take heroin, they have a feeling of euphoria, and that's because you don't feel so much, and one of the things that you don't feel is your internal organs, and so it actually makes you feel lighter, and that is going to lessen your fear, your tension. It's going to make you feel like you have more energy for a moment. As it kicks in, it's going to have a dulling of the senses and of any pain. It will decrease appetites, both the feeling of hunger, but also sexual appetite is decreased. It has a decrease in libido. It causes lethargy, all right? And eventually it causes loss of consciousness. Long-term use will lead to tolerance, and tolerance requires you to use more of the drug, and therefore you will get dependence. And in addition to dependence, you can get addiction. It means that you will have withdrawal symptoms. When you have tolerance and addiction, normally there are going to be social consequences. You are going to need to get your fix of your drug, and therefore you'll do it by stealing, by prostituting yourself in order to get money for that. This can cause to, of course, exposure to diseases like HIV, AIDS, to hepatitis C, and obviously, if you overdose, it can lead to coma and for death and death. So why does heroin have so much a stronger effect than the other ones? And so let's just go back to the images, all right? The reason for heroin having such a stronger effect is that it's less polar than morphine, all right? And therefore it can go through the blood-brain barrier much, much more readily than morphine, and therefore be in larger concentration in the brain and interact with the pain receptors more readily. Let's look again here. If we look at this structure, we can see, again, morphine has two hydroxide groups, two alcohol groups, which are very, very polar. When we look at heroin instead, those groups are significantly less polar. They're still polar, but because they don't have the OH bond, which hydrogen bonds, it is going to be less. And this is what causes it to go through the BBB much more readily and actually work. All right, thank you so much.